everyone, I hope that you are doing well. Welcome to the second video of the series Advanced Statistical Programming in R. In this video, we'll have two data sets, the housing price prediction and also the credit card eligibility. The housing price prediction, as you know, is a regression task, and the credit card eligibility classification. So my aim in this video is to show you how to train machine learning algorithms, these models, for different tasks like classification and regression. So we'll be using linear regression for the housing price prediction and then logistic regression for credit card eligibility. And I'm also planning on making another series introducing how to use these machine learning algorithms with R code to train your own models with different kind of problems. Also, you can find these models in find these datasets in the description because I took them from Kaggle, so they're open source. Without further ado, let's start. First of all, I'll be coding with you. So let's start by reading our dataset. For that, as you know, the function we are using is read.csv, and then we are writing the file name inside it, it's housing.csv. And if you set this as working directory like I did here, then you can just reach the files with their names instead of writing the full path. Now let's run this. And okay, so for exploring the data, we'll be using str function, which is writing for structure, and then the summary function, and let's see what they do. So the str function gives us all the all the features, the independent variables, and also a target variable, which is here the price. And our independent variables are area, bedrooms, bathrooms, which means that we can use all these to predict the price. And then also there's statistical values like minimum, maximum, first quartile, third quartile, and a median, mean. You can look at that if you want to look at how each independent variable is, for example, distributed. And then after training the model, maybe you can look at some explainable AI applications to see how each independent variable like affects the data, like affects the target variable. For example, do we know if when the area increases, the price increases, to these kind of things. And this was coming from the summary function and these from the str function. So we usually use both of them to get a broader view of the data we are using. And then let's calculate the average price, which will be the same here, you know, the mean of the price. It's easier to not calculate them and look at them from here, but just to show you some functions, I'll be using the median and mean functions for them. So let's do that. I'll call it average price, and then we simply call the mean function, and then housing data, which is our data name. Then we select the features of this data set, like the columns with the dollar symbol, and then we say price. And for printing, then we can say paste, and then write the average price of the house is, and then average price. Here you can see the average price, and it's the same as here, but here it's rounded version. And here we can see the more open version because this 2 is rounded to 9, so it's the same as here. Also, sorry for my keyboard noise. I really like noisy keyboards because they give me more motivation when programming. So I really like to read your comments about if you like noisy keyboards or more of quieter keyboards, and that would be great if you could share this with me. Let's continue. Now we are gonna fit a linear regression model. For that, we'll call the lm function. There are specific functions for these kind of models. If you are coming from Python, we use the scikit-learn library for that. And then from the scikit-learn library, we can call any of them we want. So they're all packed in this library. But in R, we call different functions. This can be a bit of a challenge, but it's not really hard to memorize. And then we have the price as the target variable. We first enter that. Actually, we first enter the formula. So the formula we write like this. In the formula, we write the dependent variable, so the variable we want to predict, and then this symbol, I think delta symbol, or tilde symbol, and then we enter the independent variables we want to use. So you can either put dot here, which means you'll use all the columns other than price, but you can also specify some columns you want to use, some features, like I'll do here area, bedrooms, and then bathrooms, and then air conditioning, for example. I just randomly chose them as I think these are important, but I won't be really fine-tuning the model or trying to get a good accuracy. You can do this on your own after the video if you want to. I just want to show how things work in R with machine learning. And then we enter the data, which is the housing data. And then we can get the summary of the model. Here you can see the formula we wrote with the call. And then there are some features we want to look at, for example, the coefficients and the intercept. So intercept means that if all the independent variables we chose were 0, then it would be the price prediction. And the coefficients are show the relationship between each predictor variable, like the independent variable with the other name, and target variable, which is price. For instance, a positive coefficient means that as the predictor increases, the price increases. So this was what I meant by distribution of data. You can look at that, but here coefficients give us actually the relationship, which is really nice because you can even predict without training the model from here what happens. And then we also have the residual standard. There are multiple R squared and the p-values. So R squared indicates how well the model explains the variability of the target variable, and R squared closer to 1 means a better fit. It's like a matrix we can use to learn how our model performs. It's used in basic regression tasks, which we have here, and for classification we'll use other metrics. And then p-values indicate the statistical significance of each coefficient. A p-value less than 0.05 typically indicates a significant independent variable. You can look more into these if you want. I'll be moving forward because I don't want to bore you with all these details. Let's continue. So here we are going to evaluate the model. For that, I'll use the adjusted R square and the R square. Let me write them first. These are, as I mentioned, metrics to evaluate the model for regression tasks. And then it's basically R dot squared. From the summary we get this, and the adjusted R square is the summary model. And then, as you may have guessed, adjusted R dot squared, and we can print them out. Now that's fine, let's print them out. Oops, did I think it should work, but let me see. Oh, I think you've seen my mistake before me. Yes, now we can see them. And these are the values we get. So basically in R, we fit the model like this to the variables, and this means this is training, and then we can get the residuals, the coefficients, which we'll plot in the coefficient plot, and then also the significance values we can see with these three these stars. So for p-values, as I mentioned, if they are normally the threshold is 0.05, they are less than that, then they are significant. This means, and as you've seen, these are all significant because they have 3 stars. If they hadn't got any stars or 1 star too, they would be significant too, but less significant. Can look at that. And for the R squared and adjust R squared, we got these values, and now I'm gonna interpret what these mean. Before going into that, I want to make the difference between the R squared and adjust R squared clear. If you look at the mathematical formula, I won't be going deep into that. You can look at that if you are interested. But to keep it simple, as I mentioned, R squared indicates how well the independent variables explain the variability of the dependent variable. And the adjusted R squared accounts for also the fact that adding more independent variables to a model will typically increase the R squared value, whether those variables are relevant or not. Adjust R squared only increases if the new term improves the model more than would be expected by chance. So these are all indicated in the mathematical formula too, if you want to understand this definition better, but I'll be leaving it here and talking about the values we got. So we got 56% approximately for R squared, which means that our model explains 56% of the variability in the independent variable, but it can't explain the other 44%, which means that it still has a gap where it can be improved. So the model can be improved because the R squared value could be better. It can't be really high, then it would overfit, but it can really be taken up to maybe 80%, 90%, etc. And the adjust R squared is 55%, which is basically the same. So the thing is that these values are near, which means that there isn't any problem with that because they should be normally near. And that was for the R squared and adjust R squared. Now let's predict some prices. For that we are going to be using the predict function, and it's really easy. So let's do that. We add as new data the data we want to predict. For that you can take the whole data too if you want, but I'll be taking the first 10 values. And the important thing we should remember here that the indexing begins from 1 instead of 0 in R. So we are taking not from second value, but actually the first value. Then we can look at the predictions. and also to the real values. For that, we are taking before the comma the rows, so first 10 rows basically, and after the comma the column. So for that, let's just take price so that we can see the truth labels directly. And here we can see that they are really not close, and there are a lot of errors there. So this means that our model isn't performing really well, but you can improve that. Now we are going to look at the residual analysis. Let's plot that. So in residual analysis, as we've seen in the str function, this model summary here, yes, here we can see the residuals and the coefficients, as I mentioned, some information about that. So in residuals, we put a horizontal line on the 0, which we do with ebb line. This adds lines to the plots, and h means horizontal line, and put it to the 0, and the color will be red. You can make it any color. And in residual plot, normally there shouldn't be any pattern, and the points should be randomly scattered around the 0th line. So as you can see, there are some errors here which indicate that our model isn't performing well. Now let's talk about that a bit, because it's important to be able to understand how our model performs in these kind of things. So first we have when we look at the residual plot, we should look at the pattern. Ideally, the pattern, there shouldn't be any pattern. The differences should be random and scattered, as I mentioned. But in our plot, there is a clear pattern, and you can see it. The differences seem to get smaller as we move to the right, and this means that the model might be missing something important. I wanted to make this explanation basic. You can look at more terms here. There are more complex explanations you can look at. But this is basically to see at the first sight and explain it in simpler terms. And then we look at the spread normally. The spread of the residuals, which I mean how far they are from the horizontal line, should be fairly constant. But in our plot, the spread gets smaller as we move to the right, which means that the model's errors are not consistent across all data points. And then we have some outliers too. As you see, some points are really far away from the horizontal line. This indicates that our model made large errors for these points. These might be, for example, like some unusual cases that our model find hard to explain. To give you the exact terms, we look at the pattern, homoscedasticity, and outliers normally, and the homoscedasticity is basically the spread. This is another statistical term we can use for that. Now let's move, and we'll also plot the coefficients we've looked at. And for this, I didn't plot with you, but you basically use the plot function, and then the ebb line to add the line to that and with the color. I'm not gonna plotting this with you too, to not waste time, but we use the ggplot2 library, and then we create a data frame, which we put the coefficient names, and then also the estimate, which is here. You can look at the coefficient in the model summary here, the estimate. And then when plotting, we put the term, which is the names of these coefficients of the model, and to the x-axis, and the estimate to the y-axis. As we can see here, we put the intercept and the other independent variables we've chosen, and then we basically calculate the error, and we put points for these estimates, and then put an error bar here to see how wide the confidence interval is. So if we look at this plot, we can interpret some results. So in the plot, first let's start with the intercept. Basically, the intercept value is around 0. With a large confidence interval. This suggests that the base value of the dependent variable, which is the price, when all predictors are 0, which is the intercept, as I mentioned earlier, is not well defined or varies widely. This is basically what the error bars gives us, if the model is confident in making this prediction or not. And the estimate, when it's bigger than 0, then this means a positive change, which I'll talk about. Then we have the air conditioning. The coefficient is positive, which is the dot, as you can see, bigger than 0, indicating that having air conditioning increases the price. And the confidence interval is unfortunately quite wide, indicating variability or uncertainty in this estimate too. And then we have the area. The area is around 0, but it's basically more precise because it's narrow. But we can look at that too. It seems like exactly 0, but you can also interpret it as positive. That because normally, as we know, larger areas increase the price, but as I mentioned, because the model isn't trained well, this is not really certain. I don't know how to really interpret this, but if you train the model with other parameters or other methods to get a better accuracy, then by accuracy I mean better result, because accuracy isn't really used as a metric in regression tasks, you will be able to understand the area's effect better, I think. And then the bedrooms, as we can see, they have a positive effect too, because as the rooms increase, which is the area basically, then the price usually increases too, because more area means more expensive places. If you look at the house price in websites also, this was to basically tell you how this works. And as we can see, the model is more confident in predicting more confident in like understanding the how the bedrooms affect the price. So the confidence interval is smaller, narrower, but in the bedrooms it's wider, like the air conditioning. Now, without further ado, let's move on with our second data set. For that, I'll be coding the first parts with you too. I'll be naming it the credit data, and then again we have read.csv, and the name of this was dataset.csv in my case when I've downloaded it directly from Kaggle. And the steps I take for data exploration is basically just calling the str function or the summary to see everything. You can do that in your own cases too. There are a lot of independent variables, as we can see. ID, gender, own car, own property, and the thing we want to like predict is indicated with target here. And then these are some values for minimum, maximum, as we've talked about before. Now let's calculate the average price. We could have also set median price. I think that would be better in this case. Normally, if it's normally distributed, then the median and mean value can be used interchangeably because they are really near. But if we don't really know in this case if it's not normally distributed or normally distributed, so you can look at these to have a better understanding. Statistics is in this case really important of a concept to learn. And let's say total income, and then credit data. As you may have seen, we took the median of the total income, and this should actually be income. That would be better. Sorry for that mistake. And here, to add a new column to the data set, we basically just call dollar symbol as we do for taking the already there columns from data set, and we do the same thing for adding new columns. Then I'm gonna be showing you how to use if else. We say if else, and first we enter the test, which is the condition. So if the credit data total income column, if the total income is bigger than income, median income, sorry. And then if it is, we put 1, and if it's not, we put 0, which is indicated with yes and no parameters. And then let's do this. Now there should be a new column. Let's try it out. Above median income, yes. Yes, we can see there are 1s and 0s here. And now let's with the logistic regression model. For that, we are gonna be calling the GLM function, and then enter the formula again, which is in this case the target variable as a dependent variable, and then you can put that or choose some independent variables you want to try out. You can also basically look at the p-values above from the summary the p-values we get with the training. So basically what you could do is, for example, just as an example, let's try that here. Normally I chose some random variables for that, but let's train with all of them. Then we'll look at the p-values. If they are significant, as we've seen above, they were represented with 3 or more stars, basically 1 or more stars, sorry. If the p-value is smaller than 0.05, then it's significant. We could have chosen the variables we want to use for as independent variables that way too. And then it's important to indicate the family as binomial, because this means that basically we want to get the logistic regression from the GLM function. And then let's get the summary. The good thing is we can just fit the data to the model using this function without any fit like function as we use in scikit-learn for our models when we program in Python, if you've done that. And now we've got the coefficients, the formula, and then there are a lot of. And then we have the intercept. These are the p-values. So you can see significance code, it says. And when we look, the most important ones are the family status single, not married, and age and account length, non-family, non-children. It's non-children, yes. Own property and own car a little, but not so much. You can interpret that if you know more about credit card eligibility. Also, when we look at our columns before, we just had these. We just had family status, civil marriage, married, single, not married, and separated. And here you can see when we look at the coefficients, it gives us separately, like family status, married. This is like dummy variable we create when we create dummy variables. When we give a code, assign a code to a column which has multiple values in it, and then it creates columns for each of these values. For example, when we have for family status single, married, and separated, then it creates separated, single, and married. And then for single people, it says it gives singles 1 and separated and married 0 0, for example. Then the code is 1 0 0. Basically, this kind of finite encoding seems like that, so it's a good feature to keep in mind. Now let's continue and evaluate the model. By the way, maybe to better evaluate the model, because we are going to look at the curve also, and there are a lot of features here. We could have taken the relevant features like family status, age, count length, total income, non-children, non-family. Let's maybe do that, because there are a lot of values here. Age, family. Let me check if it was family status. Normally, because we give the data, credit data, we don't need to write like this. But just to be sure I write variable names correctly, I usually do this. Then we have non-family. And then we have the total income. And let's also maybe take the family status. I think these would be all right. Well, here I did a mistake. Actually, I think you've seen my mistake. It's... Sorry for that. Now all should be fine. And if we look at that, we can see that the most importance we got. Family status, married, is not. Total income is also not so relevant. Maybe we could take that out too. Now it seems fine, but this was just for to show you, because normally total income can be a relevant value, because people that because when we have more money, then maybe it can be easier logically to pay off our credit card debts, for example. But maybe it can't be relevant too, because maybe rich people don't tend to pay off their debts. But we can't really know that unless we work in a bank. So these kind of situations is better when we have an expert by our side that can lead us. So it's not really good for all cases to just take out a value, because its p-value isn't showing a good value. It's insignificant statistically. So we should be careful in these kind of things, especially for medical data set. We should really take the suggestions of the doctor, because they are the best ones to know if this value is significant in real life for examining, for diagnosing a disease, for example. Now let's evaluate the model. We are gonna be using different metrics this time, because it's classification. I see. And the variance, as you've seen here. And now we get these values, and we'll be interpreting what these values are, and then predicting some probabilities, plotting the ROC curve, and calculating the AUC, and talking about these metrics too, and then creating a confusion matrix. And this will be all for today. So first, let's start by interpreting what the AIC and the variance is. So here, let's start with the AIC. But before that, I have to also talk about the variance too. So for the AIC, actually, because we just have one model, it's not really useful. So the AIC means the, if I'm not pronouncing it wrong, AKI key information criterion, which is basically AKAIKE information criterion. It incorporates the residual deviance and includes a penalty for a number of parameters to prevent overfitting. And here the value we have is 7,561. And normally lower AIC values indicate better models, balancing fit and complexity. So we can't really use it here. If we have trained another model, then if it had a lower AIC, this meant that we should have chosen that model because it performs better. Now when we move on to the deviance part, I have to first show you the null deviance, because we'll need that. Here in the summary you can see null deviance, which is 7,581.7. And null divines basically means represents the divines of a model that includes only the intercept, which is the when we don't have the independent variables, when they are all zero, the dependent variables value. It serves as a baseline to compare our full model's performance. The residual divines is the divines we got as here, which is 7,545. And it's the divines basically with all the independent variables included. And lower residual divines compared to null divines indicates that the predictors improve the model's fit. So basically, when we compare them here, we see an improvement of 35 when we subtract residual divines from null divines. We get approximately 35. This difference indicates how much the predictors improve the model compared to a model with no predictors. And in this case, the improvement is relatively small, but still it suggests that this improvement suggests that the model with predictors fits the data better than null model, which is a good indication. But the fact that it's relatively small indicates that the predictors do not contribute substantially to explaining the variance in the dependent variable. So this means that our model isn't really performing well. So you can, when you try with other models, you can also write the values you got in the comments and also compare different models with the AIC and also compare the same model with its null divines in comparison to its residual divines. You can do all these. Now let's move to predict the probabilities. I won't be writing this again because we use the same predict function. And then when we print that, we get the predicted probabilities basically. Here because it's a binary problem, it's not regression, it's classification. We have discrete values, not continuous like in regression, so we have 1 or 0. And the logistic regression uses a sigmoid function, as you know. So when there's a threshold, for example, when threshold is 0.5, which is commonly threshold, then when the predicted probability is above this threshold, it basically rounds up to the upper class, which is 1. And if it's below that, it rounds up to the 0th class. So we can see the predicted probabilities here, which is like confidence, we can also say. And according to that, we can maybe look from it like that. We can see that the first class isn't the model, like when we look at these values here, the model can't really predict the first class. It always predicts the 0th class when we have rounded them up, because these predictions are really close to 0, not even close to 0.5. So this means that the model predicts the 0th class with really high confidence, because normally when if you look at the sigmoid function, how it works from the internet, we like when we subtract these predicted probabilities from 1, then we get the confidence of the model basically for the 0th class, because these are rounded up to the 0th class. But we can say the confidence of a prediction for the 0th class is for example 15%. We can say that we say it's 85%. There is 89%, 87, 90 for some cases. So it's really here, it indicates some problems with the model. It can be because of the model imbalance too, but we'll look at that in the coming exercises, why the model is acting like this. Now let's look at the ROC and the AUC. Before talking about that, I want to code it with you again. So we are gonna call the PROC function, a library, sorry, and then I'll name it rock curve, and we'll put the credit data symbol, the dependent variable here, which is target, and then we'll also put the predictions. You can understand it, understand the structure kind of here, because like most metrics take first the truth labels and then the predictions, and it's not different than this. We put the truth labels, which we have as a target variable, and then the predictions, and the enter type response usually for this logistic regression. And let's plot this. Plotting is really easy in R, but if you want to make it better, you can always use ggplot. And we'll take the AUC value too. Now we got these, but before that I want to give like a background for the ROC and the AUC, because these are really important to other than the AIC, which is for comparison, for example, these really give how the model is performing. So ROC curve, ROC is the abbreviation for receiver operating characteristic. So the ROC curve is like a graphical representation of the classifier's performance across different threshold values. It shows the trade-off between two key metrics, as you can see in the axis, the sensitivity and the specificity. So the sensitivity is also called true positive rate or recall, if you have heard that. So true positive rate means dividing the true positives to true positives plus the false negatives. False negatives means that the model predicted it true, predicted it the other class. So let me explain it like that. So we have a true class, we have a positive class, and we have a negative class. Let's say positive class is 1 and negative class is 0. So true positive means the model, the truth label was 1 and the model predicted it 1. True negatives means the model predicted it 0 and the truth label was 0 because it's negative class. False negative means that the truth label was the positive class, the negative class, but it predicted it as the as the negative class. And the false positive means it's really complicated to tell like that, sorry for that. So the false positive means that the model has predicted it the negative class, but it should have been the positive class. If I'm not wrong, I have to check that to not give you the wrong information, but you can also look them up from the internet too. So for this, high sensitivity means most actual positives are correctly identified, and specificity is often present as 1 minus specificity, which is the false positive rate, but the specificity is calculated with the formula true negatives divided by true negatives plus false positives. You can, as I mentioned, look more into these. So basically what I wanted to say was, without going into much complexity, sensitivity is the matrix for the positive class, which is normally 1, but I don't know, for our case we will look when we see the confusion matrix. So it says how much it predicted correctly. So we take the predictions that had the value 1, for example, if we assume that the positive class was 1, which is the true positives plus the false negatives, and we take the fraction of it of it just the true positives, because true positives means the truth label was 1, 2, and we predicted it correctly. But there is also predictions that had the truth label 0, for example, but we predicted it 1. So we calculate all the predictions that were made as 1 and take only the true ones to see how well the model is predicting the positive class. And the false positive rate, which is the specificity is the other one. It measures the proportion of actual negatives that are correctly identified. So it's the matrix for the negative class basically. And the false positive rate, there is also a term like this. It's the 1 minus specificity, and it's false positives divided by false positives plus true negatives. The thing is the same for specificity and false positive rate, because they are divided to false positives plus true negatives, but the upper part is different. For false positive rate, it's false positives. For specificity, it's true negatives. If you are confused, you can look at the formulas from the internet too. So when we come to AUC, area under the curve, it's a single scalar value that summarizes the overall performance of a classifier. So it represents the probability that the classifier will rank a randomly chosen positive instance higher than a randomly chosen negative instance. This is the definition. You can look more into that, and it ranges from 0 to 1. If it's near 0.5, it means that it's equivalent to random guessing, and if it's 1, it means perfect. It's perfect. It's also called as perfect discriminative power. And first let's look at the AUC, because we've talked about that. Here it's near 0.5, which means that our model is performing really poorly, because it's really equivalent to random guessing, kind of. And then for the ROC curve, we have in the x-axis specificity and y-axis sensitivity. And the diagonal line, which is baseline, from 0 to 1 to 1, represents a random classifier with no predictive power, which is, as you can see here, the gray line. And then we have our models curve, which is the black curve. It represents the model's performance. And a curve close to the diagonal indicates poor performance, because diagonal is equivalent to random guessing. So here it's really near the diagonal gray line. So this means that our model is performing poorly too. These are some metrics you can look at. Now let's look at the confusion matrix. And according to that, we've gotten these values. So for the prediction and the reference, you can see that for the first class, it couldn't predict any of this correctly. But from the first class, it predicted 3 instances as 0, and from the 0th class, it predicted all of them correctly. This is we can see that here too. As I mentioned, sensitivity is the matrix for the positive class. So it is 100% here, which is, we can see here the 0th class instances were classified correctly all. No instance of the 0th class has been classified as the first class. So which means that the positive class was 0 here. And then we have the specificity, which is unfortunately 0. This is because no instance of the first class was classified correctly, and 3 instances were classified as 0. We got an overall accuracy of 0.7. which is 70%, which is normally good. It's all because of this imbalance here, because sensitivity is really good 100%, but the specificity is really bad. And when we have, for example, class imbalance, which means that, for example, the first class, here in this case, the 0th class, let's talk about that. The 0th class has a lot of values, and because we are predicting all these values correctly, this gives us a really good accuracy. And the thing that we are not classifying the very few instances of the first class doesn't really affect the accuracy. Because it's still 70%, it's good. In this case, not so good, but here you can see from here too, we had 10 instances, and the majority was the 0th class. That's why it didn't really get affected from the specificity being 0%, and 7 out of 10 was equal to 70% here. And then the balanced accuracy was 0.5. The balanced accuracy gives us a more broader view. It means like random guessing in this case the thing that it's 0.5. And I also looked at the class imbalance. I got target variables that were 0 and then that were 1, and I got some of them. And as we can see, there are 80,426 instances of the zeroth class and 1,283 instances of the first class, which indicates a really big gap between them, because there are 8 times approximately more data for the first class, zeroth class. This means that the model can be biased towards that. And there are some techniques like I use for Python, like smooth or oversampling, undersampling. You can look at all these techniques to balance out this data set, and then maybe if you just do the things we did the same without changing anything, you'll still get a better accuracy, I hope, because the imbalance was a really bad factor in this. But you can also change the independent variables, other kind of things, and try out yourself too. So that was all from me today. Thank you so much for listening, and I'll see you in the third video. Bye.